And so there's your proof. It's what's called a proof by contradiction.
I'm going to give you a really simple example of a counting proof in like combinatorics. So this is using the pigeonhole principle.
If you want to use the board too, that's
Oh,
fine. Unless you can do it verbally.
Yes,
you can do it verbally.
This is beyond easy.
Go for it.
So the pigeonhole principle is the idea that if you have 100 pigeons and 99 pigeonholes, and you say to them, I'm going to turn around and y'all going to get down in a hole. And I don't care how you do so, but when I turn around, I'm not going to see any pigeons anymore. When you turn around, you know that since there were 100 pigeons and 99 holes, that somewhere there's a hole with 2 pigeons. Okay? Now, in reality, there may be one hole with 99 pigeons, there may be 2 holes with 48 and one hiding someplace else, but this is what bothers some people, the fact that I can't show you where the hole with multiple pigeons is. But sometimes it's actually really important just to know that there is one out there, because then you can go looking for it.
And so that's what we have. I mean, physicists have experiment, for example, that might test their ideas, but we have proofs that test our ideas.
I mean, you ask me things like, what do you feel when you've just made a proof? And I think, great, have something to show my advisor. if I work more, then maybe after finishing after like getting rid of all the mistakes, I might be able to publish a paper.
Do you ever listen to Bloomberg or CNN? Do you ever hear how many people are sure of very opposite things?
Proof is a formalization, an indicator, like many indicators I used, in economics and the like.
You can pull out certain things and come to certain conclusions, or you can pull out other things and come to other conclusions.
I'm precisely interested in the possibility that that particular closure that a formalization represents is excluding things that are either there, they have always been there, but they have not been factored into that proof, or that there are new things that cannot be captured by that particular closure, that particular indicator, that particular proof.
Is it malicious? No, I think these people are doing their best. It depends. There's so much information. It depends on what you wish to use, and mostly that's determined by the conclusion you want to reach.
All of this raises really deep questions.
People get in trouble when they take as true things that they've been told on good authority are true, but they don't understand the way it works.
What kinds of objects are these numbers? If they're abstract entities, if they're non-physical, abstract, platonic entities, how is it that we could have any kind of access to them at all? How is it that we could learn anything about them? We don't interact with them physically, so on and so forth. These are really good questions. These are really deep questions.
So there's a tendency for mathematicians to want to understand, at one point, the proofs of what they use.
And the answer is going to be something like, it has to do with my experience with toasters.
Well, I think mathematics, I think that people's brains have developed in interaction with the world, and therefore the kinds of ideas that we have often are sort of consonant with what happens in the world.
You say the toaster isn't working because it's sad, okay? And you try to take an approach based on that turns out to be much less successful than saying, I want to look at the internal mechanism, I want to see what's banging into what and what's not connected to what, and my idea is that's going to be more useful for getting the toaster to work again.
That is right. But I would argue that you need empirical experience to understand the concepts.
Yes.
I don't think the concepts themselves, once they are understood, leave you any place to maneuver them.
All the stuff that we do and the way we learn, it evolves and it comes from creating. So zeros and ones, math.
I don't think it's my experience of living in the world that creates this. I think it's just that the way the human brain is made, which is built up of the experience of life over however many millions of years, has created a brain that sort of works in a particular way.
There are basic mathematical structures that I don't want to speculate how we get there, It's part of our genetic endowment, or our genetic endowment working in this world. But the intuitions are so strong that I must take them as basic.
I think what God has created, He then puts the formulas and we then learn formulas of what has already been created.
In that sense, I'd say that largely mathematics is about understanding the world. And there's a sense to which all these things are out there to be described. And while today's version may be mathematically modeling the effects of an earthquake or the synapses between our nerve cells and how much firing goes off, that may be on a much quote-unquote higher level than understanding that zero exists, but we're still trying to figure out what's going on and what it all means.
Like, it's all interconnected. Like, the tools from, I'm going to use some technical terms, but just different areas of that. The tools from algebraic geometry happen to apply to studying topology.
And a lot of the times, you find this connection, our basis is in reality. But you don't want to necessarily, want to build up off of this basic reality. You want to, I think, a lot of times you come back down.
Or you study the topology of various systems, and then that happens to explain in dynamics like the behavior of solitons. Like when you blow a smoke ring, why do the smoke rings persist? That's related to some topological behavior.
You don't not only want to build up the layers of abstraction, you also want to see if you can come back down either to reality itself or to something else that has been discovered.
It's a little bit of which came first, the chicken or the egg, when you talk about like physics and math. Sometimes mathematicians come up with stuff and it seems like freakish, who needs this? And then 20 years later someone says, oh wait, this perfectly explains blah blah blah. And other times a physicist comes up with a question and says, well, I don't know what I'm doing with this, maybe there's some math that can help.
The Big Bang was like an old flash bulb in a picture, and the flash is still resonating in the universe. You look various ways and see how strong the residue of that flash bulb is, and it gives you kind of an idea how far things are different ways. And people are trying to fit that together to say, what's the geometry of the universe?
It's a little bit hard to imagine how the three-dimensional universe might be connected because we don't have a place to stand outside the universe and look at it. So it's a little bit easier to imagine how a two-dimensional universe might be connected. So you might imagine some creature living in the plane. So some stick figure living in the plane, and can walk around in the plane. But this is not it's stuck in the plane. He can't get out of the plane. So the easiest thing to imagine is that it's this blackboard extends out forever, and it's just a single body that you could go off and explore. But there are other possibilities too. This fellow might be living on the surface of a ball, where if he goes far enough in one direction, he eventually comes back on himself from another direction. Or there might be a more complicated surface, like the surface of a donut, which is a little bit more complicated, or say the surface of an object like this, which where there are various different ways where you could walk in one direction and come back on yourself, either around here or maybe around here, or a whole bunch of different ones. I mean, this is